So let's get started. So here is the first algorithm that we are going to look at. This algorithm is called as KNN, and that seems like a weird name for an algorithm. We'll talk about what the expansion of this is in a minute, but that's the last thing, right? So let's first try to understand the algorithm and then let's say give it a name later. Okay, to simplify the question, let's say we just have a name, age, and salary of customers in our database. Again, it's John, Mary, and Smith. And let's say you didn't have the other details, you just had age and salary, and now you want to make a decision. I'm simplifying the problem further because it's easy to visualize when you have lesser number of features as opposed to lot of features, right? So and I'll tell you what it means to visualize this in a second. We'll actually visualize this data set. Of course, the name does not really matter, right? So you're not going to give a loan to a person based on his or her name. So what really matters here are age and salary, right? So if a person, the typical wisdom is that the older somebody is, the salary is perhaps higher, and now depending on what age that person is, maybe depending on the salary slightly higher, and then perhaps that person will return the loan, pay the loan back, and so on and so forth, right? So that's our typical model that we have in our head, and we somehow want to formalize that as an algorithm, as a method to arrive at how to make decisions for Hari, if I know Hari's age and salary. For now, in this example, again, I'm going to ask you to pause and think. If Hari's age is 28 and his salary is 16,000, and now looking at John, Mary, and Smith's data, how would you make a decision whether Hari should be given a loan or not? What would be your answer? Are you going to give, if you are the manager, are you going to grant a loan to Hari or not? If you are, then how did you make that decision? If you are not going to grant, fine, but how did you make that decision? The algorithm or the model that you used in your head to make this decision, that's the more important thing, right? So you're somehow using information such as age and salary to make this decision, and you're not just using Hari's age and salary, but you're also using John, Mary, and Smith's age and salary to somehow come up with some decision rule, so to say, in your head, and I am interested in knowing what that decision rule is, right? So here I am going to give you one way to solve this problem. As we said, this is what is called as a KNN method, and it does the following. So what we are going to do now is just visualize the data set that we have as our training data, right? So how do I visualize this? There are, in this but simplified example, there are just two features. One is the age feature, one is the salary feature. So now I can think of age as one axis and salary as one other axis. So think of the x-axis as the age and the y-axis as salary. And now here is a point, right? So this point, which I am calling as John. Now what does this point mean? This point means, John's age is, in this particular case, 29, and John's salary, which is the y-axis, is $12,500. So John becomes a single point in this two-dimensional space. This is a two-dimensional space. The one dimension is the age dimension, the other dimension is the salary dimension. So there are infinite points in this two-dimensional space, and every point corresponds to some value of age and salary. So every person in our database becomes one point in this two-dimensional space. In this case, John becomes this point. Mary's age is less than John's age, so Mary will become a point here, which is 27, and Mary's salary is more than John's salary. In fact, it is significantly more. It is $30,000. So that becomes Mary's point. Smith is somewhere here. Smith's age is 36. He's older than both John and Mary. So he's towards the right in the x-axis. Whereas Smith's salary is much lesser than both John and Mary's salary. So it's just $4,500. So Smith is here. Now let's look at what the color of these data points mean. Well, John and Mary are in green, whereas Smith is in red. What does that mean? Why have I colored it like that? Well, it should be clear. So John's label and Mary's label is S. Both John and Mary, when they took their loan from this bank, paid the loan back on time, whereas Smith is in red because Smith failed to pay the loan back, right. So, Smith is in red, John and Mary are in green, and now we have a new customer who is Hari, whose age is somewhere between the age of John and Mary, in this case 28, and his salary is 16,000, right. So, closer to John than Mary. So, 16,000. So, that is Hari. Hari does not have a color yet, right. So, meaning we do not know at this point if Hari will pay the loan back or not, because the loan has not yet been granted. So, now the question is, should Hari be granted the loan or not based on this? In other words, should we color Hari as green or red? Given that John and Mary, who are also points in this two-dimensional space, have green color and Smith has red color, here is Hari, and now we want to ask the question, should Hari be colored green or colored red? Now, visually, if you look at it, now there's a lot of ways of thinking about how to give a color to Hari in this case. I am going to suggest one particular way which is based on the following fact, following hypothesis, right. So, if Hari was in fact a point in my data set, what do I mean by that? If there had been a person in my bank who had exactly the same age as Hari and exactly the same salary as Hari, then depending on whether that person paid the loan back or not, I can make a decision for Hari. That is, if my test data point, which is in this case Hari, is already there in my training set, then the problem becomes easier for me, because I know somebody who has the same set of features as Hari in terms of age and salary in this case, and I can hope that Hari's behavior in paying back the loan is going to be very similar to this person's behavior who has the exact same age and exact same salary, right. So, that is my hypothesis in this case. Now, if that happens, then I would just output the label for Hari as exactly the same label as this person whose features are exactly the same as that of Hari's, who's present in my database or in my historical data. Now, unfortunately, in this particular example, that is not the case, right. So, we do not have somebody with age 28 and salary $16,000 in this data set. Now, still we need to make a decision, right. So, you cannot say that there is nobody with the same age and salary, so I cannot decide, right. So, as a bank manager, you have to make a decision. Now, the question is, how can you make this decision, right. So, what would be the most natural thing to do when you do not have a person with exactly the same features in your data set? Well, one natural thing to do is that you choose somebody who is closest, and I am going to put this in quote, right. So, closest, choose someone who is closest to Hari in the training data. We do not have Hari in our training set, but we have somebody who is closest to Hari in our training set. Well, by closest, I mean that now, because each data point, each person becomes a point in this two-dimensional space, there is a potential way to measure distances in two-dimensional space, right. So, given 2 points in two-dimensional space, x1, x2 or x1, y1, let us call this x1, x2 and y1, y2, or let us not use y because that is typically used for labels. Let us say x1 dash, x2 dash, these are 2 points. How can I measure distance between these 2 points? Well, the simplest way to measure distance would be to look at the length of the line segment joining this point x to this point x prime, right. And that would be what? That would be just x1 minus x1 prime squared plus x2 minus x2 prime squared, and then you take a square root. This is what is called as the Euclidean distance between 2 points and I'm sure all of us know this based on basic geometry, right? So what I'm saying is that given 2 points, there is a way to measure distance between these 2 points, right? Now, which means that the notion of closest then becomes meaningful, right? So now for given this new person Hari, who corresponds to a new point in this 2-dimensional space, there is a way to measure distance of Hari to everybody else, distance of Hari to John, to Mary, to Smith. Now, what will I then do? I don't have Hari in my data set, so I'm going to pretend that the closest person in my data set is in fact my proxy for Hari. And in this particular example, who would that proxy be, right? So in other words, who has the closest distance to Hari? You can pause and think, but that's very easy visually. You can see that it is John, right? So by distance wise, John is closest to Hari. And the moment you have figured out that John is the closest guy to Hari, now John, you ask the question, did John pay back the loan or not? In this case, it happens so that John did pay the loan back. So which means that you can assume that Hari will also pay the loan back. And because now your algorithm, then this is our algorithm, has decided that, you know, the proxy of Hari, the closest person in my data set to Hari, who is John, paid the loan back. I'm hoping that Hari will also pay the loan back, and so as a manager, I'm going to, you know, grant the loan to Hari. So that is the algorithm, and this, because this algorithm uses the closest person in my data set. In other words, this person uses the nearest, closest, nearest are all same, nearest neighbor in my data set. Well, so you are basically thinking of who is the closest point in the training set to the test data point, which is also called as the nearest neighbor, and you are just outputting the label of your test data point as the label of the nearest neighbor. So in this case, it would just be a green for Hari. Fine. So the algorithm is called as KNN. I have already told you what the NN is. The NN stands for nearest neighbor. Now we'll come to the K part in a minute. But before that, let's ask the question, what can go wrong in this algorithm? In other words, is this a good algorithm? Right? So for instance, is this the algorithm that you came up with when I asked you to pause and think? If not, it may or may not have been the algorithm that you came up with. If not, let's think of this as a potential algorithm to solve the learning problem of supervised learning and ask, can this algorithm go wrong? I think this is an important question you should ask for anything, you know, in science, right? So you are putting out something there, and you should be the biggest critic of your own, you know, methods, right? So you should ask, you know, can this fail, right? So will this fail? And you should try as much as possible to figure out conditions where your own algorithm will fail. Only then you will convince yourself whether it's a good algorithm or a bad algorithm, right? So if it fails for a lot of cases, then perhaps it's not that good an algorithm. Maybe that will give you a hint as to how to fix it, and so on and so forth. Here we ask the same question, right? So here is the algorithm. Given a test data point, find the nearest neighbor in the training set, output the label of the nearest neighbor as the prediction for the test data point. As simple as that. Question is, when can this algorithm fail? Pause and think about this, and now I'll tell you potentially what might go wrong with such an algorithm.